A surprising number of high-value stones are missed not because they're rare, but because they don't look the part. In roadside gravel piles, stream beds, and even landscaping runoff, collectors routinely step over stones that would easily fetch hundreds if properly identified, simply because they lack the expected brilliance or coloration. The truth is, most valuable stones in their natural state appear dull, coated, or deceptively ordinary. Consider the upper Midwest and Appalachian regions, where garnets and sapphires, sometimes mistaken for iron-rich pebbles, hide in glacial deposits and alluvial fans. These stones don't announce themselves with gem-like clarity. Instead, they signal their value through density, habit, and subtle luster shifts when wet. The collector trained to see these first-level cues can isolate potentially valuable material before lifting a single tool. It begins with observation. In gravel beds, stones with sub-rounded but still angular edges often originate from harder material, resistant to weathering, hinting at garnet, corundum, or spinel. A quick water rinse can expose a vitreous or even greasy luster. Unlike quartz, which flashes white or smoky and has a glassy surface, denser stones tend to look thicker or oilier under sunlight. A simple squeeze in the palm may hint at higher than average weight, an intuitive first pass that often reveals more than it seems. In creeks, especially those draining metamorphic or volcanic zones, you're not just hunting by sight, but by context. A single translucent red grain nestled among quartz and feldspar pebbles might signal a garnet-rich vein upstream. Similarly, deep green pebbles with fibrous texture could suggest nephrite jade, especially near serpentinized zones in the Pacific Northwest. These early reads aren't about certainty. They're about creating a short list of candidates worth testing further. Even landscaping gravel and road aggregate in the Southeast and Rockies can carry non-native gems from distant quarries. Discarded quartzite mixed with magnetite-rich fragments may contain corundum or even beryl from upstream commercial cuts. The missed opportunity here isn't rare, it's recurring. Knowing how to scan these spaces with intent transforms accidental glances into directed discovery. And yet, the moment you pick up a stone that feels heavier than it should, you're entering a decision tree. What next? How do you test that instinct without wasting time on lookalikes? The next step is low-cost, fast, and often portable, built entirely around visible traits and gravity. That's where visual triggers take over from intuition. Not all stones worth testing advertise their value with color. In fact, some of the most valuable rough materials, like sapphire, garnet, and jade, can appear dusty, opaque, or deceptively plain until you know what to look for. The initial assessment is visual, yes, but not casual. A trained scan looks for anomalies in luster, texture, translucency, and shape, clues that separate just a rock from something worth pocketing. Luster is your first field cue. A greasy or waxy sheen under natural light can flag nephrite or jadeite, especially when paired with fibrous or compact texture. Unlike quartz's clean, glassy break, jade tends to show a dense, felt-like interior if fractured. Garnets, on the other hand, may flash submetallic or resinous in rounded creek-worn forms, especially almandine or pyrope types. The trick is to look for what doesn't quite match the surrounding matrix. One dull red pebble in a sea of gray can justify a closer look. Translucency often helps refine this guess. Holding a candidate stone to the sun or a flashlight beam can reveal its internal light behavior. High-quality jade, for example, allows light to penetrate and glow slightly, whereas low-grade serpentine or soapstone stays opaque. Even partial translucency in green or white stones is a promising sign in the field. For garnets or sapphires, edge translucency, where thin edges glow red or blue, may indicate gem potential, especially in stream-polished material. Shape also matters. Habit, or the natural crystal shape, is often distorted in stream beds, but some forms survive. Garnets may show dodecahedral or trapezohedral hints, rounded but symmetrical edges. Corundum, sapphire, and ruby often appears as stubby hexagonal prisms, sometimes with flat basal terminations. If a stone feels geometric without being angular, it's likely worth closer inspection. But even the best-trained eye can be misled. Volcanic glass can mimic luster. River-polished quartz can suggest translucency. That's why visual indicators alone are the start, not the proof. Still, visual triage is critical. It helps narrow the hundreds of stones in a square meter of gravel to 5 or 10 that justify further testing. Most first-time collectors wander without realizing that the land itself is speaking, quietly but clearly. Valuable stones don't appear randomly. They travel, settle, and concentrate in predictable geologic settings shaped by tectonics, erosion, and time. Learning to read terrain, without needing a degree, can mean the difference between scooping gravel and isolating a cluster of gem-grade material. Start with elevation and drainage. In the Appalachians, for instance, garnet and corundum can be traced from metamorphic bedrock down into stream beds. The key lies in the pattern of deposition. Broad, meandering creeks with exposed gravel bars are ideal sorting zones. Heavier minerals settle in inside bends or downstream of natural obstructions. These pockets, called placer traps, are prime for corundum, zircon, and even the occasional sapphire. In glacially influenced terrain, such as Minnesota, Wisconsin, or parts of New York, look for erratics and till zones where ancient ice sheets dropped a chaotic mix of materials from hundreds of miles away. Here, you'll find garnet-rich schist, milky quartz, and even beryl pebbles scattered like geological breadcrumbs. In these cases, following the heaviest, reddest, or most angular stones ups your chances of discovering origin-linked specimens, material that hasn't traveled far from its source. Volcanic regions in the West tell a different story. Nevada, Idaho, and eastern Oregon host opal and fire agate zones where silica-rich fluids filled voids in rhyolite flows. These often weather into soft, chalky outcrops, easy to overlook unless you know the structure. The opal hides inside vugs or seams, shielded by crusts of white or tan matrix. A thin pocket knife or chisel test can sometimes reveal an iridescent play of color beneath what looks like baked mud. In ultramafic terrains like California's Coast Ranges or Wyoming's greenstone belts, nephrite jade forms within serpentinized zones. These belts are identifiable by their deep green soils, scattered magnetite, and distinctive slick rock surfaces. Often, jade is found near faults where tectonic pressure sheared and altered rock chemistry over millions of years. Such zones can produce hefty boulders of river jade, rounded by time, or angular blocks still clinging to their host rock. One of the most overlooked environments is human-modified terrain. Quarry tailings, road cuts, and dam spoils. Many commercial gravel operations in the southeast and southwest unknowingly haul gem-bearing rock from upstream sources. If you notice unusually dense stones, or bright colors where they shouldn't be, take note. These sites often allow hand-picking with permission, and they reset with every new load. The terrain doesn't just guide the search, it dictates your tools, safety, and strategy. Lowland creeks require different gear and timing than high-altitude jade fields or roadside quartz piles. But no matter the region, the terrain tells you what's plausible and what's a waste of time. And once you've narrowed to a promising zone, how do you begin testing what you've picked up? The fastest indicator might not be color or luster, but magnetism. What most collectors miss is that some of the best clues aren't visible. They're magnetic. In areas rich with gem-bearing deposits, a simple magnet can separate the ordinary from the potentially valuable in seconds. It's a test so quick and lightweight that many professionals run it before they even wipe the dirt off a stone. And when you know what you're looking for, the magnet doesn't just find iron. It maps a trail of heavy indicator minerals that often ride alongside garnet, corundum, and even diamond-hosting rock. The test begins with a dry batch of stones or pan concentrates. After a visual sort, you pass a neodymium magnet, small, strong, and easily pocketed, gently over the material. A slight twitch, a slide, or even a jump toward the magnet signals the presence of magnetic minerals. But this isn't about collecting magnetite. It's about reading what magnetite is trying to tell you. In several parts of the eastern U.S., especially the Carolinas, Georgia, and parts of Vermont, magnetite and ilmenite often accompany red garnet and blue sapphire in metamorphic gravel fans. Their presence doesn't guarantee gem-grade material, but it narrows the field dramatically. This signal becomes even more useful in terrains associated with ultramafic or kimberlitic geology. In Wyoming, parts of Montana, and certain zones of Arkansas, a magnet reacting to dark, fine-grained pebbles might be pointing to ilmenite or chromite. Minerals often found in the same erosion paths as pyrope garnets and other diamond indicators. These stones, though not magnetic themselves, travel in the same density range and accumulate under similar hydraulic conditions. Where magnetite gathers, the likelihood of heavier, gem-grade material increases sharply. But the magnet isn't a final answer. It's a field filter. One response means nothing. Patterns, however, speak volumes. If multiple particles in a specific bend of a creek or a scree slope cluster show magnetic behavior, it may indicate a localized feeder zone upstream. And because magnetic minerals are often much denser than quartz or feldspar, they tend to accumulate in placer traps, the inside curves of slow-moving streams, plunge pools, and natural riffles. Knowing where to sweep and reading a consistent pull across multiple samples gives the collector a silent compass that points toward potential. It's also a fast way to avoid wasting time. In sediment lodes dominated by granite, sandstone, or limestone, a complete lack of magnetic response suggests low odds of gem companions. That doesn't mean nothing's present, but it resets your expectations. The beauty of this test is how little effort it takes to change your direction before committing deeper field hours. It's also essential in safety-conscious collecting, in areas where time is limited, due to terrain, water flow, or wildlife. A magnet pass can let you make smarter choices under pressure. Still, even after isolating magnetic hot zones, not every stone that stays behind is valuable. Density is the next filter, because while the magnet tells you what might be nearby, only gravity can tell you what's worth keeping. What most beginners underestimate is just how quickly gravity can do the hard work. If you let it, a well-run pan test doesn't require gold, just the right kind of density. Whether you're working a high creek in North Carolina or a dry arroyo in Idaho, the pan becomes your first portable laboratory. It's here that heavy, high-value stones like garnet, zircon, sapphire, or even spinel reveal themselves not by shine, but by refusing to move. The logic is simple. Heavier minerals resist motion when agitated in water. By screening material through a number 20 or number 40 mesh, roughly between 0.85 millimeters and 0.425 millimeters, you eliminate the oversized distractions and let physics isolate the most promising grains. With a bit of clean water and steady wrist work, the light quartz, feldspar, and organic debris flush away, leaving behind a dense concentrate that is physically different under your fingertips. These are your suspects. If you've sampled from a region known for metamorphic or volcanic rock, say, near a mica schist outcrop or rhyolite dome, the odds increase that what's left in the pan isn't just heavy, it's valuable. In practice, a good pan test doesn't end with one pass. After the initial rinse, you tilt the pan to expose the bottom layer. What remains should show hints of color, structure, or luster. Deep reds from almandine garnet, glassy grains of zircon, or dense, dull black particles of ilmenite. It's not uncommon to mistake this final layer for black sand. especially when magnetite dominates, but a practiced eye learns to see the flashes of non-magnetic heavies trapped among them. Each of these residue stones tells you something. Red, angular grains may suggest garnet with cutting potential. Translucent colorless pebbles with oddly high density might flag zircon or topaz. If you're near jade-bearing terrain, dark green fragments that don't float and resist abrasion could signal nephrite. The pan concentrates give you something visual, tactile, and repeatable. 3 traits that make any field observation scientifically valuable. And when several pans pulled from different spots all produce similar residues, you're building a density map by hand. Beyond diagnostics, the pan test also creates a decision point. If your concentrates are consistent and visually promising, it may be time to grid the location for repeatability. If they're not, but a few heavies linger, it may justify moving upslope or cross-creek to track the source. Either way, you've now moved beyond collecting random stones. You're now chasing a pattern that can be tested, mapped, and eventually sold. But weight and behavior in water are only part of the story. Some stones hide their identity not in movement, but in resistance. And for that, the next frontier is hardness. The moment you can scratch one stone with another, you're already doing field mineralogy. Hardness and density aren't abstract values. They're tactile, testable, and critical in separating lookalikes from the real thing. After a visual inspection and pan concentration, these 2 traits often provide the first definitive filter between common quartz and more valuable materials like corundum, spinel, or topaz. And the best part? You can run these tests with tools as simple as a pocket knife, ceramic tile, or sandpaper. Hardness is measured on the Mohs scale, which ranks minerals by their resistance to scratching. Quartz sits at 7, meaning it can scratch glass, but will be marked by anything harder. Corundum, ruby and sapphire, ranks at 9. Diamond is the only natural substance harder. In the field, this means a piece of silicon carbide sandpaper, typically rated around 9, becomes an instant screening tool. If a stone visibly scratches the sandpaper, but shows no wear itself, you may be holding something that deserves serious attention. Conversely, if the stone dulls or powders under the sandpaper, it's likely quartz or a similar low-value material. Scratch testing isn't foolproof, though. Some stones fracture before scratching clearly. Others leave ambiguous marks. That's why density, the weight in hand, matters just as much. Picking up a garnet or zircon after handling quartz all day often produces an immediate reaction. It feels heavier than it should. This weight differential isn't imagined. Zircon, for instance, has a specific gravity of 4.6 to 4.7, while quartz is just 2.65. You can test this more precisely using a basic water displacement setup. Fill a graduated cylinder, drop the dry stone in, and calculate its volume shift. Then divide the stone's dry weight by its volume in milliliters. If the resulting number exceeds 3.5, you're likely dealing with something denser and potentially more valuable than quartz. Together, hardness and density eliminate dozens of false positives. Glass, for instance, often mimics topaz or spinel in appearance, but can be scratched at around 5.5 and has a low density. Similarly, many feldspar variants have good color and shimmer, but scratch under 7 and feel light in the hand. On the flip side, a pebble that scratches quartz survives the sandpaper test and feels unexpectedly heavy could be an uncut sapphire or a dense variety of garnet. Those stones deserve further testing and possibly professional appraisal. Even nephrite and jadeite, which often appear dull and unremarkable, reveal their value here. Nephrite usually falls between 6 and 6.5 on the hardness scale, but its density, around 2.9 to 3.0, is noticeably higher than surrounding host rock. Jadeite pushes even higher, often reaching 3.3 to 3.5, especially in gem-grade material. These values are just high enough to separate them from serpentine or soapstone, their most common imposters. These simple tests mark a turning point. Up until now, your evidence has been circumstantial, sight, weight, magnetism. But once a stone passes scratch and density tests, it graduates from interesting to possibly valuable. At this stage, the question shifts from what it is to how you can verify and prove it. And sometimes, under the right light, a stone reveals that answer by glowing in the dark. When the lights go out, certain stones speak, and others stay silent. Ultraviolet fluorescence, long used in gem labs and mining operations, can reveal properties invisible to the naked eye. But in fieldwork, its role is more suggestive than decisive. A stone's reaction to UV light can flag hidden chemistry, but it's not a standalone test. It's a clue, a flicker that says, look closer. The most immediate use of UV light in the field is screening for diamond. Many natural diamonds fluoresce blue under long-wave UV, especially those with trace nitrogen impurities. In contrast, moissanite, a common diamond simulant, often shows green or yellowish hues, and in some cases doesn't fluoresce at all. But the overlap is messy. Some real diamonds show no fluorescence. Some synthetics mimic it too well. That's why serious collectors and buyers treat UV as a supporting signal, never a final answer. Beyond diamond, UV can illuminate other minerals worth noting. Scheelite, a tungsten or occasionally mistaken for quartz, glows bright blue-white. Calcite and fluorite varieties fluoresce in reds, oranges, greens, and purples depending on their trace elements. Even certain feldspars, like moonstone and labradorite, can emit soft glows that hint at internal structural anomalies or specific geographic origin. In some garnet species, rare orange-pink responses under shortwave UV can suggest spessartine content, though this is far less common and usually requires laboratory conditions. Field use requires the right tools. A handheld long-wave UV lamp, ideally with a filtered lens, is the safest and most practical for general identification. You'll want to work in near total darkness, which can be tricky in remote or outdoor conditions. A simple blackout bag or a deep shade tarp can help create a mini lab in the back of a vehicle or tent. Always avoid direct eye exposure to the bulb. UV light can damage vision with prolonged contact. Likewise, don't rely on smartphone UV filters or camera flashes. They're too weak and imprecise for mineral work. What UV testing offers is rapid triage. If a stone fluoresces unusually, that doesn't confirm its identity, but it raises the probability that it contains trace activators like chromium, manganese, or rare earth elements. These elements can enhance color, increase market value, or point toward a specific geologic source. And that's often enough to justify moving a stone up the testing chain. But UV also works in reverse. If a supposed ruby doesn't fluoresce under long-wave UV, it may not be ruby at all. Synthetic spinels, colored glass, and other fakes often fail this check, even if they pass the visual exam. Likewise, dyed stones, especially quartz or agate, may show patchy or unnatural fluorescence, betraying treatments invisible under daylight. The real lesson of UV testing is restraint. It's a tool for confirmation, not revelation. It won't tell you if a stone is valuable, but it will often tell you whether it's worth further investment. And if the glow matches the theory, you're one step closer to proof. At a glance, quartz, glass, and diamond can all look equally brilliant. Under a loupe, even experienced eyes can be fooled by precise cuts or strategic inclusions. But when you touch them with the right tool, the truth emerges fast. Thermal conductivity is one of the few field-accessible properties that reliably separates natural diamond from its imitators. It's not subjective, and it's not visual. It's physics, and it doesn't lie. The principle is straightforward. Diamond conducts heat better than nearly any other natural material. A thermal conductivity tester, often called a diamond tester, uses a small metal probe to detect how quickly heat dissipates through the stone. When applied to the surface, real diamond pulls the heat away instantly, triggering a sharp response on the device. Most fakes, especially glass, cubic zirconia, and quartz, fail this test immediately, registering as poor conductors. It's a rapid binary. The stone either dissipates heat like diamond or it doesn't. But there's a catch. Moissanite, a lab-grown silicon carbide, is nearly as thermally conductive as diamond. So much so that it can pass as diamond on older testers. That's where electrical conductivity becomes essential. Unlike diamond, moissanite conducts electricity. A dual-mode tester that checks both thermal and electrical response can flag moissanite quickly. If the thermal probe says diamond, but the electrical test also pings positive, the stone is not a natural diamond. These testers, now handheld and relatively affordable, have become indispensable not only in gem labs, but also in serious field kits. Their use is especially important in areas known for alluvial diamonds, like parts of Arkansas near the crater of Diamonds State Park. There, quartz and calcite crystals often form with high clarity and mimic the look of rough diamond. But quartz has low thermal conductivity, and calcite reacts weakly or not at all. A quick probe check prevents wasted effort on clear imposters. Thermal testing also helps with less obvious suspects. Some zircon and topaz crystals, when highly transparent, can be mistaken for low-grade diamond rough, especially in stream-worn form. But zircon, while dense, does not conduct heat in the same way. Topaz, similarly hard, registers cold on the probe. These stones may still hold value, but not in the thousands per carat range that a verified diamond commands. Even if you're not chasing diamonds, thermal tools reveal behavior that supports broader mineral ID. Corundum, for example, has a moderate thermal response. Glass and most synthetics lag far behind. Over time, a tester becomes more than just a yes/no device. It forms a behavioral fingerprint for every type of stone you encounter. The real value of thermal and electrical response isn't just speed, it's confidence. Once a candidate passes both tests appropriately, your probability of error drops dramatically. And in the field, where time, permits, or weather may limit access, that kind of certainty is priceless. But what happens when a stone passes all your tests, only to fail in the lab? The next topic reveals how false positives slip through, and how to catch them before they cost you. No matter how sharp your eye or thorough your toolkit, every serious collector eventually meets a stone that passes the field tests, and still turns out to be worthless. False positives are the great leveler. They mimic color, density, hardness, and even luster with near perfection. But under lab scrutiny, they reveal what they truly are: common, altered, or synthetic materials dressed up to deceive. Glass is the most pervasive culprit. In riverbeds, tumbled shards of old bottles or industrial slag can appear water-worn and gem-like, flashing vivid greens, blues, or even reds. Their rounded forms and clarity make them easy to mistake for beryl, tourmaline, or even sapphire. In denser colors, they pass the heft-in-hand test. Some glass even scratches at a Mohs hardness of 6 or higher, narrowly brushing the range of useful gemstones. But the giveaway comes in the fracture. Glass tends to conchoidally break with smooth, curved surfaces, and under magnification, internal bubbles or swirl patterns betray its origin. A diamond tester typically rules it out in seconds, but for someone relying on visual inspection alone, it's an expensive mistake waiting to happen. Zircon is trickier. It's a naturally occurring mineral, sometimes even valuable, but often mistaken for diamond due to its high brilliance and density. With a specific gravity above 4.5, it feels heavy and can show stunning clarity in stream-worn form. It scratches glass, flashes white and blue, and even passes rudimentary visual tests for diamond mimicry. Yet it's not electrically inert, and on closer inspection, shows double refraction, something diamond never does. A loupe will reveal doubled back facets, or a shadowed girdle line. In some cases, heat-treated zircon will show unnatural colors, bright canary yellow or neon blue, that hint at man-made intervention, reducing its value significantly. Then come the dyed stones, porous agates, quartzes, and jaspers that have been soaked in chemical baths to exaggerate their natural tones. These pieces often show intense, even coloration, particularly along fracture lines or pores. In the field, their vibrant hues stand out against muted natural palettes, drawing the eye immediately. But once sliced or polished, the dye bleeds or pools, revealing artificiality. A quick acetone wipe can sometimes lift the surface color. Under UV light, many dyed stones fluoresce inconsistently or reveal patchy areas where the treatment didn't penetrate. These stones can still be beautiful, but they're not natural specimens, and their market value drops accordingly. Even lab-created corundum, which passes both hardness and density tests, can deceive if it's tumbled or coated to appear natural. Flame fusion rubies and sapphires are notoriously common in old tailings or international gravel mixes. Without access to spectroscopy or advanced microscopy, they can pass as natural finds. But under strong magnification, curved growth lines or gas bubbles give them away. Features never found in Earth-formed sapphire. The danger with false positives isn't just in wasted time. It's in misplaced confidence. A collector who misidentifies a stone once is likely to do it again, compounding the error. Worse, selling a misidentified stone, intentionally or not, can burn trust, invite returns, or trigger legal consequences. That's why the next layer in the process isn't about testing more stones. It's about testing your process. Gridding, repeating, and validating in controlled sampling zones separates one-off curiosities from traceable mineral occurrences. The difference between a lucky find and a sustainable yield comes down to one habit: repeatability. In field mineral exploration, it's not enough to locate a single promising stone. Without recording where, when, and how it was found, and testing that spot again under controlled conditions, you're not prospecting. You're guessing. The moment you treat your site like a dataset, patterns emerge, and those patterns are where real value begins. Gridding is the foundation. Whether you're working a creek bend, a hillside, or an old tailings pile, divide the area into testable squares. 10 by 10 meters is a good starting point. Each square gets its own sample pass. Pan concentrates, visual scans, magnet sweeps, and density checks. Use GPS, if available, or triangulate against fixed landmarks. Record slope, sun angle, recent weather, and water flow. These may seem like details, but they shape how and where heavies settle. A high-quality garnet in grid A2 means more when grid A1 is barren, and A3 shows a cluster of magnetic heavies. Now you're building a map, not just of stones, but of probability. This approach reveals more than distribution. It shows source direction. In slope environments, dense stones migrate downhill, but rarely far. In water, they follow the current's drop zones. If one grid keeps yielding garnets, sapphires, or heavy indicators, the upstream quadrant becomes your next focus. Over time, this data forms a geologic story, where the material came from, how far it moved, and whether it's worth chasing upstream or concentrating downstream. Each repeat sample confirms or challenges that story, and prevents you from misreading a single outlier as a trend. Recording also protects against false memory. A collector returning to a site months later will forget whether the best finds came from the west-facing bend or the shaded pool under the sycamore. Photos, bagged samples with labels, and a field notebook with sketches preserve the integrity of your discovery. It also protects you if you intend to sell or partner with a claim. Having a paper trail of repeated hits supports your credibility and raises buyer confidence. More importantly, repeat testing weeds out anomalies. One brilliant zircon in a pan could have rolled in from a construction site, been dropped by another collector, or come from an isolated fragment of a non-native lode. But 5 pans in the same 5-meter square yielding the same type of heavy grains? That's not a fluke. That's a target zone. And a repeatable find in the same grid after rain, snowmelt, or seasonal shift proves something even more powerful: that the deposit reloads. This is what transforms casual collection into ongoing extraction. In high-stakes collecting, especially in diamond or jade-bearing terrain, repeatability also guides when and where to cut. Do you invest in lapidary gear now? Do you pay for lab certification? Or do you expand the grid before committing funds? Without repeatable field data, these decisions remain speculative. But when you have it, when Grid C yields heavies 3 trips in a row, and Grid D shows heat-reactive sapphire shards, there's no guesswork. There's only next steps. And that next step, for many, is the big decision. When is it time to pay for official testing? The answer isn't just about stone quality. It's about timing, risk, and knowing what the labs can and can't tell you. There comes a point in every serious search where curiosity collides with cost. A stone that's passed the visual, weight, magnet, pan, and scratch tests begins to whisper real potential. But to turn a find into a verified asset, whether for sale, cutting, or trade, you'll need proof. That's where certification comes in, and knowing when to send a stone to a lab and what to ask for can make the difference between profit and sunk expense. Not all stones are worth certifying. Labs charge based on service level, turnaround time, and the complexity of the material. Basic identification reports may run $50 to $150, while full gemological grading with origin analysis, spectroscopy, and treatment detection can exceed $300 per stone. For high-value material, top-grade sapphire, jadeite, diamond, or rare beryl, that cost is a fraction of potential return. But for mid-range finds, certification can eat most or all of the resale margin. The first decision isn't whether the stone is beautiful. It's whether it shows enough signs of premium traits to justify investment. Size and clarity are the first gatekeepers. A rough garnet under 1 carat, no matter how red, may not be worth lab work. But a 5-carat, inclusion-free crystal that shows facet potential? That's a candidate. Likewise, jade that holds translucency when backlit and passes scratch and density tests may be worth confirming as nephrite or jadeite, especially if you're in a region where both occur. A diamond-like crystal that passes thermal, but not electrical response deserves lab verification, especially if double refraction is absent and specific gravity matches. But timing matters too. Submitting a stone too early, before you understand your site, grid, or potential for repeats, can backfire. A one-off certification for an outlier find may confirm the stone's identity, but it won't answer the bigger question: is this a fluke, or is there more? Conversely, certifying too late, after cutting, polishing, or exposure to environmental damage, can introduce ambiguity. Many labs prefer working with uncut material, where inclusions and growth structures are intact. A preform report can increase the value of a cut stone by proving it was natural and untreated. When you decide to proceed, the lab you choose matters. Reputable institutions like GIA, Gemological Institute of America, AGL, American Gemological Laboratories, and IGI, International Gemological Institute, offer standard methods, reproducible results, and market-respected documentation. For stones of regional significance, like Montana sapphires or Arkansas diamonds, State labs or university geoscience departments may offer lower-cost analysis with excellent reliability. Always ask for full disclosure services, treatments, syntheses, and origin estimation when possible. These all affect market value. Certification isn't just about selling. It also protects you. A documented origin, mineral identity, and treatment history makes it harder for a buyer to claim misrepresentation. In some markets, especially international ones, a lab certificate is required for import, auction, or insurance. It also shields you from undervaluation. There are many cases where sellers let stones go for pennies on the dollar simply because they lacked proof of grade. A verified stone opens doors, but which one you walk through changes everything. Once testing confirms you've got a legitimate find, the next decision is just as strategic. Do you sell it raw, invest in cutting, or leverage the data and location for something even bigger? Each path carries different risks, timelines, and payoffs, and knowing which suits your material and your goals can define your success as much as the stone itself. Raw stones, if clean and sizable, often sell faster and with less overhead. Many collectors, cutters, and small-scale jewelers prefer uncut specimens because they preserve full weight and offer creative freedom. In the US, platforms like eBay, Etsy, and specialized gem forums provide ready markets for raw material, especially if it's paired with test results, scale references, and geographic origin. A well-lit photo of a backlit garnet, combined with a specific gravity number and scratch data, can outperform a polished stone with no documentation. Provenance adds value, but only if it's repeatable and verifiable. Cutting changes the equation. If a stone shows clarity, color consistency, and stable hardness, lapidary work can multiply its market value. A 10-carat rough sapphire with inclusions might sell for $500. If cut cleanly into a 5-carat eye-clean gem, its value could exceed $5,000. But cutting is not free. Precision faceting demands experience, equipment, and risk. Some stones shatter, others lose more weight than expected. Unless you're a trained cutter, outsourcing is standard, and that requires trust and often upfront cost. It also means waiting. If your stone doesn't finish well, or if the market shifts before sale, you may lose more than you invested. Then there's a third option, rarely discussed outside advanced circles: selling the rights to the data or location. If your find came from a previously undocumented deposit, or if your grid work, pan results, and sample suite suggest a repeatable source, you may have something more valuable than a single gem. You may have a lead. Small-scale mining outfits, lapidary cooperatives, or even academic institutions may pay for access, data licensing, or exploratory rights, particularly if the site falls outside protected zones and shows multi-mineral potential. In this scenario, you're not selling stones. You're selling discovery. This path takes more work up front. Detailed sampling logs, maps, repeat tests, and ideally a few certified specimens. But it pays in leverage. A hobbyist collector who can show consistent results across 6 creek bends or 3 distinct zones of ultramafic terrain becomes something else. A scout, a prospector, a source. And that can lead to partnerships, co-ops, or shared extraction contracts, especially in regions where land use allows recreational prospecting with mineral rights. Presentation is key across all 3 channels. Clear, zoomed-in photographs, reference scales, transparency about flaws, inclusions, or limitations. A stone with a crack can still sell if the buyer knows what they're getting. But even a flawless piece can stagnate if poorly lit, overdescribed, or disconnected from context. And in every case, test results matter. A thermal probe reading, hardness score, and specific gravity note may be all that separates your listing from 100 others. Behind every high-value stone sold, there's one simple truth. Someone wanted it badly enough to pay. But what drives that desire? And what commands the highest prices is rarely just beauty. The gem market moves on four primary pillars: color, size, clarity, and provenance. Understand how these shape buyer behavior, and you stop selling stones. You start selling value. Color leads the conversation. It's the first trait noticed, and often the last to be forgiven. For sapphire, rich royal blues command premiums. For garnet, deep wine reds and vivid orange spessartine hues draw attention. A stone that's technically rare, but visually washed out will underperform every time. Buyers are not laboratories. They respond emotionally. That's why a neon green tourmaline from Maine might outprice a flawless colorless beryl, even if the latter is objectively rarer. Stones with saturation, clean, intense, and consistent, always attract more serious offers, especially when they show well under both daylight and artificial light. Size comes next, and here, thresholds matter. A 1-carat sapphire may sell, but a 3-carat stone with equivalent color and clarity moves faster and fetches more, sometimes exponentially. This is not a linear game. Crossing the 5-carat mark in any colored stone shifts it into a different tier of competition. For jade, even more so. Translucent jadeite over 20 grams enters collectible, even auction-level, territory. But bigger is not always better. If size comes at the cost of visible inclusions or poor symmetry, buyers drop out. The value curve bends dramatically when quality and size meet cleanly. Clarity is where many field-collected stones stumble. Natural inclusions, gas bubbles, rutile needles, fracture lines, are expected, but they must not dominate. Buyers tolerate flaws that are hidden in the setting or that don't affect transparency. What they resist are large feathers, surface-reaching cracks, or clouding that dulls the stone's light return. The best stones are eye-clean, flaws visible under magnification but not with the naked eye. However, some inclusions, like the shimmering silk in certain sapphires, can actually enhance value if they create desirable optical effects like asterism or chatoyancy. Then there's provenance, the story behind the stone. A clear blue sapphire is valuable. A clear blue sapphire with confirmed Montana origin, pulled from a documented claim and certified untreated? That's a premium stone. American buyers especially are leaning into domestic sourcing, and ethical origin is now more than a trend. It's a pricing factor. Similarly, a nephrite jade from Wyoming with documented grid sampling and visual fieldwork can outprice a larger, cleaner piece from unknown terrain. Provenance isn't just about honesty. It's about rarity, location branding, and narrative. It gives a collector something to point to and a buyer something to trust. When all four factors align, vivid color, substantial size, clean interior, and documented source, the price ceiling lifts. Stones that meet 2 out of 4 might still sell, but often at wholesale or hobbyist rates. Those that hit 3 of 4 can enter gallery, auction, or boutique markets. Only those that hit all 4, backed by test data and visual presentation, become investment grade. Still, even knowing the rules, sellers make mistakes. Often, they underprice or overpromise, due to urgency, guesswork, or bad advice. The next topic exposes exactly how collectors lose thousands by misreading the market, and how to avoid being one of them. Every gem collector hears a version of the same story. A stone pulled from the creek, tested with care, and sold for a modest sum, only to appear months later, recut and certified, on the auction block for 10 times the price. The mistake wasn't in finding the stone. It was in misunderstanding what it really was. Undervaluation doesn't just cost money. It erodes the return on every hour spent in the field. And the tragedy is, it's often preventable. The most common undervaluation error is haste. A collector gets excited, confirms basic traits, hardness, luster, density, and sells quickly for a few $100s, eager to cash in. But without full spectroscopy, UV reaction, and inclusions mapping, they never learn that their find was untreated, high-clarity corundum, exactly the material that labs mark as premium. Buyers, especially experienced dealers and cutters, recognize this immediately. They're not just buying the stone, they're buying the gap in your knowledge. Another major factor is weight loss through cutting. Rough stones lose 30% to 70% of their mass during faceting. If you sell by carat without understanding cut yield, you might base your price on 12 carats of rough, when in reality, it will only yield 4 carats of finished stone. But those 4 carats, if clean and vivid, may be worth exponentially more per carat than the raw material. When you underprice the rough, you're not just giving away volume, you're handing someone else the margin. Market awareness is also critical. A collector in rural Oregon might compare their opal to commercial-grade material from Australia and assume low value. But certain U.S. opals, particularly those with full play of color, can command prices equal to or higher than their overseas counterparts when provenance is clear and quality is strong. The same is true for Montana sapphires, North Carolina garnets, or even high-translucency nephrite from Wyoming. Domestic stones are gaining traction precisely because they're traceable and local, and yet many sellers treat them like secondary goods. Lack of documentation kills pricing power. If you can't prove hardness, specific gravity, or origin, even with basic notes and phone photos, you invite low offers. Buyers see uncertainty as cost. And in gem sales, the burden of proof always falls on the seller. Even a single-page summary with field photos, GPS coordinates, and simple test results can shift buyer confidence and triple the offer range. A seller who offers nothing but a visual description invites skepticism and discounts. There's also the issue of false humility. Many collectors assume that because they're not professionals, their finds must be low-grade. This becomes self-fulfilling. They undersell, accept poor offers, and never pursue certification. But a stone doesn't care who found it. If it meets the standards, optical, structural, geologic, it holds value, regardless of whether it came from a state park or a university trench. The final undervaluation trap is failing to control timing. Markets move. If you sell too early, before gem shows, before holiday demand, or before auction season, you leave money on the table. Conversely, holding too long without certification or proper storage risks damage, fading, or cracking, all of which lower value. Smart sellers manage the cycle. Test quickly, document fully, and list when buyer energy is highest. The good news? Once you've learned to avoid these traps, the next step is strategic. Finding the U.S. regions where high-value stones actually surface with consistency. And that means understanding which states are producing and what terrain features make them so productive. Not all land is created equal, especially when you're chasing gems. Across the United States, specific states and geological zones consistently yield valuable stones. But the reasons aren't always obvious. It's not just about known mines or popular parks. It's about the intersection of bedrock type, erosion history, and access. Understanding where to look and why those regions produce can shortcut months of wandering into a focused, high-yield strategy. Montana leads the way with sapphires, especially in the Rock Creek and Missouri River zones. These stones are not just plentiful, they're uniquely American in provenance and coloration. While their hue is often lighter than traditional Kashmir or Sri Lankan stones, their untreated nature and traceable source give them serious market appeal. Most occur in river gravels, sorted by glacial and fluvial processes. Panning in these regions can reveal pale blue, green, or even pink corundum, stones that may not look like much until cleaned, cut, and certified. North Carolina holds a different kind of wealth. Its ancient metamorphic zones produce garnets, kyanite, and even corundum, often in micaceous schist. The Kawi Valley region is especially known for ruby and sapphire finds, many of which come out dull and weathered, but reveal vivid color when sliced. Stream placers fed by decomposing host rock are the key, especially after rains. And unlike many states, North Carolina has several dig-your-own sites where collectors have pulled stones exceeding 5 carats. Idaho and Oregon share volcanic pedigrees that yield opals, fire agate, sunstone, and jasper in quantity and variety. The Owyhee region, in particular, is famous for picture jasper, scenic slabs with incredible polish potential. In southern Oregon, the Ponderosa and Plush areas yield sunstone, feldspar with copper inclusions that flash red, green, or even Schiller effects. These stones are often surface gathered or collected with minimal digging, making them ideal for beginners who want a real chance at market-grade material. California offers a mix of jade, tourmaline, and bonitoite, the state gem. While much of the best tourmaline historically came from San Diego County, the Big Sur coast yields some of the country's finest nephrite jade. These pieces are typically found in beach boulders or near serpentinized cliffs and often require tide-timed hunting and physical labor to extract. Meanwhile, bonitoite, a brilliant blue barium titanium silicate found in San Benito County, remains one of the rarest gems in the world. Legal collecting is limited to a handful of paid sites, but even tiny crystals can sell for premium prices. Arkansas deserves mention for a very different reason: diamond. At Crater of Diamonds State Park, the only publicly accessible diamond-bearing site in the world, visitors can legally search for and keep any diamonds they find. While most are under 1 carat, a few stones over 5 carats are recovered every year, often by tourists with no prior experience. The diamonds here are typically octahedral, sometimes coated in a thin layer of volcanic soil, and respond well to thermal testing in the field. In the Northeast, New York's Adirondacks yield labradorite, garnet, and occasionally zircon. These stones occur in high-grade metamorphic terrains, and although the climate limits year-round access, the mineral diversity is unmatched. Garnet mines in the region once supplied industrial abrasives, but gem-grade material still occurs in tailings and nearby creeks. Each of these regions has one thing in common: a consistent geologic logic. Whether it's ultramafic belts, glacial till, or volcanic seams, the terrain dictates the opportunity. But terrain also shapes risk, especially when weather, wildlife, or land ownership enter the picture.